I often overlook the usefulness of the circle node in computational design to define distances and tangencies. However, I was recently looking at a problem for modeling a series of ramps where the circle node proved to be quite useful. In this problem, a series of connected ramps was needed, but their exact placement was the design element, so they needed to be free to move. But of course, they needed to be connected one to another and connect the predefined floor elevations. So in a problem like this, I always try to think about what is known and what does the designer need to be free to control. In this case, the floor elevations or heights were already established in the OpenBuildings floor manager, represented by H1, H2, H3, and H4 in the diagram here. Of course, these could potentially change during the design process. The ramp width would be a variable represented by W and would be consistent for all the ramps. Initially, I presumed that the length of each ramp would be determined freely by the designer based on coordinate systems or points placed in the model. But in fact, the ramps would at least have a minimum slope, meaning that the length of each ramp would be determined by the height multiplied by that slope. So while I wanted to locate the start points and end points of the ramps with coordinate systems that could be freely moved by the designer, the length of the ramps was not actually free. By using a circle with a radius defined as the length of the ramp, I could create a curve that the next coordinate system was tied to. Now, given that the ramps are not just a line, but they do have width, I created a third variable that defined the diagonal of the ramp, R1 in this diagram. This is the actual radius used by the circle. So let's take a walk through the script. First, I use the building and floor nodes to get the floors from the floor manager. This gives me the floor heights and coordinate systems or planes at each floor elevation, and if changes are made to the floor manager, they will be picked up in the GC script. Next, I added a coordinate system at floor 0, which represents the start point of the ramp. This is free to move anywhere in the XY plane. Next, I added a center point for the first circle, which will define the length of the first ramp. This point needed to be projected to the next floor plane so that the circle is drawn on the next floor plane. Now, I also needed to create a few variables. I created a slider node that would define the slope as 1 to the value on the slider, such as 1 to 10 or 1 to 12 or 1 to 20. Next, I created an expression node to calculate the length of the first ramp. I used the height of floor 0 multiplied by the slope value. I also added a slider for the width of the ramp. This will be the same for all the ramps. Then I created another expression to calculate the diagonal of the ramp. I'm simply using a squared plus b squared equals c squared, or the square root of L1, the length, squared, plus w, the width, squared. With those variables, I can define the first construction circle, defined by the diagonal length of the first ramp, and which will control the placement of the start point of the next ramp. Now I added a coordinate system to define the start point of the next ramp. It uses the technique by parameter along curve. The curve being the circle, and the t-value is free so that the designer can freely move the coordinate system along the curve, maintaining the correct length of the first ramp. Now I simply repeated the last few transactions, creating a new center point projected to the next floor plane, expressions that calculate the length and diagonal of the next ramp and the corresponding circle, and so on for each of the ramps. I now have 5 points or coordinate systems that control the start and end points of each ramp. Any one of these points can be freely moved along its path, maintaining the correct length for each ramp, while also modifying the remaining ramps. So circles proved a good way to maintain the correct distance between my construction points for the ramps. I'm also going to use a circle to help define the edges of the ramps. The points or coordinate systems are actually defining the knuckle or joint between two ramps, one which is going up and one which is going down. So, as I discovered, this is not as simple as drawing a line string between these points. I need to create line strings that go from the point to the outer or inner edge of the ramp, defined by the next point and the ramp width. Since the angles between the ramps are not necessarily known and need to be free to move, this proved to be a little bit tricky. But again, I was able to use circles to define the width of the ramp, and then draw lines to the tangent points on the circles, giving me rectangular ramps with the correct width and length. So let's take a look. So first I added a circle at each of the coordinate systems with the radius defined by the width variable. Next I needed to project a point from one coordinate system tangent to the next circle. I did this with the technique project at tangent to curve, and used a list of all the coordinate systems and circles to do all the points with one node. Now, there are actually 2 points that could be projected, so I used a reference point placed in the model to keep the first set of points on the lower side of the curve. Then I used these new points and the coordinate systems to create a series of lines that represent one side of the ramp. I then repeated these steps to create points on the opposite side of the circles and generate lines for the opposite edge of the ramp. Once that was done, I could create a ruled surface between the lines, creating the actual ramps. So the circles will maintain the width of the ramps and the connection between each ramp. I can go back and modify the placement of the coordinate system and realign the ramps. I can also open the control panel and modify the variables. Change the slope, for instance, which in turn will make all the ramps longer. And change the width. This changes the radius of the circle, changing the tangent points, and everything remains correctly aligned.
If you found this video helpful, please give it a like. If you want to see more such series, consider subscribing to our channel. Thank you, and see you next time.